Hello everyone, I am Srivatsa Madva, working as Assistant Professor in Department of Electrical and Electronics Engineering, SGBIT Belagavi. I welcome all the students and friends for today's class. The subject that we are dealing here is transmission and distribution. The subject code is 18EE43 for 4th semester students in as per the VTU syllabus. So the concept that I have chosen today is inductance of three-phase lines with equilateral and symmetrical spacing. Let us represent the three-phase lines using the figure which is shown in the figure 1. That is, it is representing the three-phase line with equilateral and symmetrically spacing. Here you can observe that let us consider three conductors and name it as the conductor A, conductor B and conductor C, and it is placed such a way that at the corners of an equilateral triangle, which means all the three conductors are equilaterally spaced, and they have to be placed symmetrically, which means the distance between all the three conductors should be D. If you consider here the conductor AB, the distance is D, the conductor BC is also having the distance D, and conductor AC is placed at a distance D. And let us consider the radius of the conductor as I represent over here for 1. Let all the three conductors be of radius R. Okay, equal radius R. So in order to find out, the derivation is with respect to the calculating the inductance of a three-phase line. So in order to find the inductance is given by flux linkage per current. So keeping in that mind, first let us try to find out the value of flux linking with respect to any of the conductor. So for example, let us start with conductor A itself, because so considering the conductor A, then if I am trying to find the flux linking with respect to the conductor A, then there will be the flux linking with conductor A will be because of three terms. That is, the first one will be the flux linking with respect to its own conductor, and then the flux linking with respect to the conductor B, and the flux linking with respect to conductor C. The flux linking with respect to conductor A itself means the current which is flowing across the conductor A, that is, I can represent it as IA, the current which is flowing with respect in the conductor A can be represented as IA. Similarly, the current across the conductor B can be represented as IB, and the current across C can be represented as IC. So taking these currents, so that is IA across the conductor A, IB across the conductor B, and IC across the conductor C. So let us try to find out the flux linking because of these three conductors across, these three currents across these three conductors with respect to conductor A. The flux linking with respect to conductor A can be notified as psi A, which means the flux linking with respect to conductor, it is conductor A, can be given by, as I mentioned earlier, it is with respect to the three terms, that is, the flux linking with respect to the conductor A because of the current which is flowing across the conductor A, that is given by 2 × 10⁻⁷ IA ln of 1 by R dash, because it with respect to its own conductor. So it obviously depends on the radius of the conductor. Then with respect to the conductor B, the second and third terms will be with respect to conductor B and conductor C. So I am interested in finding out the flux linking in the conductor A because of this is called as first is self one. The first term which I highlighted, that is, the flux linking with respect to its own conductor is considered to be the self inductance, and the flux linking because of the adjacent conductors, that is B and C, these can be considered as mutual inductances. So whenever I am trying to find out the mutual inductance, that is because of the current which is flowing across the conductor B, it produces a certain amount of flux which gets influenced on the conductor A. So there will be flux linking on the conductor A because of conductor B and conductor C. The second term, that is the flux linking in conductor A because of the current in conductor B, can be written as 2 into 10 raised to minus 7. The current is IB. This remains constant. I have taken as constant here. 2 into 10 raised to minus 7 into the term, the second term. This is very important term. That is IB ln of 1 by D. The only difference is the current. The first thing is the difference is current, because as it is with respect to the conductor B, the current across the conductor B will be IB, and the distance, the mutual inductance, that is ln of 1 by D. This is the distance between the conductor A and B. You can notify from the figure, which is represented in the figure 1. Similarly, whenever I am trying to find out the flux linking because of the conductor C, current in the conductor C, I can notify it as in the third term 2 into 10 raised to minus 7 IC. IC is the current which is flowing across the conductor C, and ln of 1 by D. So this gives me the equation 1. So I found out the flux linking in conductor A, but it is having three different, actually there are three terms, that is with respect to current IA, with respect to current IB, and the third term is IC current. In order to find out the flux linking with respect to conductor A, I can make some changes such that I will be ending up with only one unknown term, that is current IA. I want to express these terms IB and IC, which are having common parameters, that is ln of 1 by D is common when I am comparing both ln 1 by D is common in the second and third term. So if I have to resolve them, means if I take it out, then it will be IB plus IC. Okay, so I will be attaining, if I take them out, then it will be IB plus IC ln of 1 by D. So in the first term, it is comprising of IA ln of 1 by R dash, and then in the second term it will be IB plus IC ln of 1 by D. So in the three-phase system, what will be the concept is, let us assume the three-phase system is balanced one. So I can, using that concept, I can write a current equation such that IA, IB, IC will result in the value of 0. Okay, IA, IB and IC will result in 0. This is our equation 2. Using this equation, I can rewrite the value for IB plus IC in terms of IA. It is, whenever I am shifting it on the right hand side of in the equation 2, so I will be obtaining the value as IA is equal to minus of IB plus IC, which means the value in the above equation, I want to substitute the value of IB plus IC in terms of IA. So what I will do is IB plus IC, if I just move the minus sign to the left hand side, it will be IB plus IC is equal to minus IA. So I found out a representation for IB plus IC combination in terms of IA. So that my equation becomes, the first equation becomes completely dependent on with respect to the conductor A current as well as flux linking. So in the next equation you can observe here, for psi A, I just try to substitute the value of IB plus IC in equation 1. So what I attained as 2 into 10 raised to minus 7 IA ln of 1 by R dash. This was the first term, and the second and the third term I resolved and tried to substitute in terms of IA. What I obtained as minus of IA ln of 1 by D. So now both the terms, the first and second term, are in terms of current IA, the common term. So I can take the common terms out such that my equation becomes my equation, whatever I wanted to find out, IA, it is completely dependent on the single term, that is IA. Fine. So this is only the unknown term. If I am having this one, then I can easily find out the value of flux linking. So in the first and second term, the common terms are IA, so I will take it out. So I can represent it as 2 into 10 raised to minus 7 IA. So ln of, there will be, I will be left with two important parameters, that is ln of 1 by r dash and a ln of 1 by d. Well, how it will be, I will just write it here. So it will be 2 into 10 raised to minus 7. So if I take IA as common outside, so it will be ln of 1 by r dash minus ln of 1 by d. So I can write this as, so as we all know the basic operations on the ln of 1 by r dash minus ln of 1 by d. I can take the division. Whenever it is subtraction, it becomes in terms of division, that it will be 2 into 10 raised to minus 7 IA. I can rewrite it as ln of 1 by r dash divided by 1 by d. Okay, I can represent it this way, such that if this will go for the numerator side, so it becomes, finally the equation becomes 2 into 10 raised to minus 7 IA ln of d by r dash. This is the equation for flux linkage. So I obtained the first portion because I wanted to find out the inductance. Inductance equation is given by LA is equal to psi A by IA. IA remains same, but I found out the value of psi A. From this is represented in equation 4. So after substituting in the equation in order to find out the inductance, that is the psi A value is 2 into 10 raised to minus 7 IA ln of d by r dash. Okay, we obtained from the equation 4. And the denominator I am having IA. So let us keep IA as it is. The common term is IA, so I will strike it out such that I will be finding out the value of inductance with respect to the conductor A. It is given as L subscript A, which means the inductance of a conductor A is given as 2 into 10 raised to minus 7 ln of d by r dash. So this will be, obviously inductance will be expressed in terms of millihenries, but whatever the equation I have found out, it is inductance per phase value. Okay, this you have to be very much sure because it will be helpful for solving the problems. Similarly, as the concept is of three-phase lines with equilateral as well as a symmetrical spacing, which means the value of inductance for all the phases, that is conductor B and conductor C, remains the same. So the inductance with respect to conductor B can be represented in the equation. I will call this equation as equation B, this as equation A, and similarly for the conductor C, it remains the same as equation C. Further, we can solve for the next. We can solve a problem on this particular concept using a three-phase line for equilateral as symmetrical spacing. As follows. The problem statement is a three-phase transmission line 100 km long has its conductors of 0.6 cm diameter, which are spaced at the corners of equilateral triangle. Each side of equilateral triangle is of 100 centimeters. The arrangement is shown in the figure, as shown in the figure here, and he is asking find the inductance per phase of the system. So, as per the statement of the problem, it is comprising of a three-phase system with equilateral and symmetrically spaced conductors. So, the given things from the the three-phase system are the length of the transmission line is of 100 km length. So, I have represented here, and the diameter of each conductor he has given as 0.6 centimeters, and these arrangements, the three-phase conductors are placed equilaterally. So each side of the equilateral triangle is of 100 centimeters. So from the figure you can notify here, I have the distance between two conductors, that is nothing but, as per our derivation, it can be notified by the value d. And let A, B, C be the conductors, and it is as per the given things, the diameter of each conductor is of 0.6 centimeters. Okay, and he has asked to find out the value of inductance per phase of the system. So keeping in this point, so what is the formula to be used here? Let me put it in the form of formula. So what is the formula that we require? The formula that we require are, the first one, I have to find out the R dash value that is given by 0.7788. It is a constant value which should be multiplied by R. This is radius of the conductor. This is first and foremost formula which we will be using. And then the next is inductance per phase. Okay, that let us consider one conductor. That is, inductance per phase is given by 2 into 10 raised to minus 7 ln of capital D by R dash. Okay, so this is the second formula that I will be requiring. So without wasting time, let us look after the problem solution here. So directly he has provided the D value. So in order to attain the value of inductance, there are two unknown terms, that is the value of D and the value of R dash. The value of D he has provided, he has given the value of D, but I have to calculate the value of R dash. The first and foremost, I have to begin with the value of R dash. That is, the value of R dash is given by the equation 0.7788, which has to be multiplied by R. So let us substitute the value here, that is 0.7788 into the resistance. R is the radius of each conductor. So let us find out the value of radius here. The diameter he has given as small d, that is 0.6 centimeter. But as I want the value of radius, that is R, is d by 2. That will be 0.6 centimeter divided by 2. So R will be 0.3 centimeters. That can be expressed as in terms of, I want to express this in terms of meters. So how I can write it? It is 0.003 meters. So 0.3 centimeters. So the resistance is, the radius of a conductor is 0.003 meters. So I want it in the form of, so R dash what will be the R dash value here? Using the calci, I found out the value to be 2.3364 into 10 to the power minus 3 meters. So this is my first thing. So the next, this 2.3364 10 raised to minus 3. So the next step is, in this equation, the next step is inductance. That is nothing but inductance per phase. So it is given by LA, that is 2 into 10 raised to minus 7 ln of D by R dash. Now, as I am having both the values, I can substitute the values here, that is 2 into 10 raised to minus 7 ln of, what is the value of D? 100 centimeters. But I want it to express in terms of meters. R dash is 2.3364 into 10 to the power minus 3 meters. 100 centimeters. Try to convert and express in terms of meters. 100. 0.01. Okay. 100 centimeters is equal to, I want it to express in terms of meters, so it will be 1. 100 centimeters is equal to nothing but, it can be expressed in terms of meters, so it will be 1 meter. Okay, so what will be the value of LA here? The inductance value after solving, what will be the value? but a slight adjustment I should have to be acquiring in this one, because as it is 2 raised to, it will be in terms of millihenry per meters. Okay. As I want the entire thing has to be calculated per kilometer, I have to per kilometer, right? It has to be, I am converting millihenry per meters into millihenry per kilometer. So in order to convert this one, what I have to do is I have to multiply this entire term by 10 to the power plus 3, okay, such that it appears to be per kilometer. This from meter to kilometer conversion. So I have to multiply by 10 raised to 3. So what happens in the equation? It appears to be 10 to the power minus 4, 10 raised minus 7, 10 to the power 3. So it will be 10 to the power minus 4 ln of 1 divided by 2.3364 into 10 to the power minus 3. So I will be attaining the value as 1.2118 into 10 to the power 10 to the power minus 3 Henry per kilometers. So, or also it can be expressed as 1.2118. Always go for 4 decimals, 4 places after the decimal. So 10 raised to minus 3 I can remove. So I can write it as 1.218 millihenry per kilometer. So this is a standard one. So this is what I wanted. The LA value I found out to be 1.2118 millihenry per kilometer. But what is the length of the transmission line? It is 100 kilometers. So I have to find out the entire inductance of the transmission line. So in order to find out the inductance of the transmission line of length of, I will write transmission line in short form as TL of 100 kilometer line length. So it will be, I have to multiply this LA into the distance of length of the transmission line here is provided as 100. So I have to multiply by 100. 1.2118 into millihenry. I have to express in terms of Henry per kilometers. So what it will be? What will be the value? Just multiply, and you will be obtaining the value as, I want it in terms of, so kilometer, when I am multiplying with respect to the kilometer, with respect to the distance, the kilometer, this kilometer gets cancelled. So I will be left with only the Henry. So the inductance, always expressed in Henries, it will be 0.12118 Henries. Thank you.